With 38 slots, 0 and 00 are green, odds are red, and evens are black. So part A, determine the probability it falls into a green slot. So we know there are 38 slots. The only options that are green are 0 and 00. So 2 out of the 38 are green. So you divide that, you get 0.0526. Interpret the probability. You could say a lot of different things. There's a 5.26% chance of a green, or only 2 of the 38 chances are green, something along those lines. B, the probability it falls into a red or a green. Okay, can it be both red and green? No. So or means add, and we are just straight adding these together. So when I look, the odd numbers are red. So how many odd numbers are there? So 18 out of 38. How many are green?
2.
So we get 20 out of 38, or 0.5263. C, the probability that it is 0, 0, so that's only one of them, or red. So or means we add. How many reds are there?
18.
So we get 19 out of 38, or 0.5. D, determine the probability it falls into both the number 31 and a black. So 31 is an odd number, but it tells us the odd numbers are red. So can it be 31 and black? No. So if it's not possible, that's 0. We call that an impossible event. Because there's only one ball, it falls into one slot. The 31 slot is red, so it cannot be both 31 and black.
We pick up points if we don't put 0, we just put cannot happen.
I mean, if I say the probability, you should probably give me a number. All right. Number 9. So are we okay with making the probability model? You have to add up all your numbers and divide each one by the total. So that's your probabilities. Part B, it wants to know, is it unusual to live between 18 and 79 years old? So we look 18 to 79, and our probability distribution that we just made on part A, what did you get for that probability? 0.121. I had 0.1213. Do you guys know how I got that? So what's the definition of unusual? Less than 5%. So if it's over 5%, it's not unusual. So just want to know if this is unusual. No. The probability is over 5%. Do we need to look at any others on B? Or on 9, sorry. Absolutely. So part D, what's the probability that the individual will not want to live 100 plus years? So you have 2 options. And when you did your probability distribution, you know, we had those different x's and the probability of each. You got the first one to be 0.1213, 0.2522. Okay, so this is from part A, but I'm going to throw it up here so I can talk about it. Okay, so one way to look at it, if you don't want to live to be 100 plus, you are one of these other 3 categories. So you could add those 3 numbers together to get it. You could also say, okay, not wanting to be 100 plus is everyone except this group, so you could do it as a complement, 1 minus that. We should get the same answer either way, 0.6266. So sense? So either add up the other three categories or just do 1 minus that one. All right. Problem 10. So we are talking about this lovely table here. So part A, the probability of being post-term. I don't know why it won't let me paste this over.
No, just grab and drop it.
It's not letting me. I don't know why. This is how I always do it. That would be easier than I could write all over it. It's still won't let me. Interesting. Okay, let's look at it from here.
Just take a screenshot and drop it in.
That's what I was trying to do. So, the probability of being post-term. So this is out of everyone. So we have to look at our grand total number of people. So our grand total is this 3,948,828. We agree with that, and we want those that are post-term. So that's the 225044. So we just divide those. And we get our 0.056. I left 99, but if you said 0.057, that's also okay. B, this one is again out of everyone. So the denominator is the same. We want those that weighed 3,000 to 3,999. So I'm looking 3,000 to 3,999. So that's my 2,596,000. And we get 0.6576. Does everyone understand where those numbers are coming from? Part C. This is an and. It's not a given. Unless it's a given, it's still out of everybody. So I want weighed 3,000 to 3,999 and post-term. So I can look directly at my table. 3,000, 3,999, and post-term is the 160,354. So we get 0.0406. D is an or. Okay, so I'm going to cheat a little bit. I don't want to write this denominator over and over again, so I'm going to put it all in one big fraction. Okay. So first we need those that weighed the 3,000 to 3,999. Okay, we did that in part B. That was the 2596802. Plus, we need those that are post-term. We did that in part A. 225044. But have we double counted anyone? Yes, we double counted those that are both in that weight group and post-term. That's what we found on part C. So you could set it up from these fractions. You could just take part A plus part B minus part C, and that would also give it to you because we're subtracting off our overlap. So we do the first plus the second minus ones we double counted. Or probability from A plus the probability from B minus the probability from C, because we'd already done those individual things. Is that one okay? D, now I got into the givens. When we do givens, it is no longer out of everyone. So when I'm looking at this, my denominator is the condition. So we're finding the probability of term given it weighed less than 1,000. So weighed less than 1,000 is my denominator. Look at that table. how many were in the less than 1,000 age or weight group? Cover up the rest of the table. We are only looking at that top row. And from that top row, we want the ones that were term. So we look at the term in the top row, and that's 179. So then we divide those. We get 0.0066. F. We wanted the probability, they were at 3,000. 3,999 given post-term. So my denominator is my condition. That is the post-term. So everybody look at your table. Find the post-term column. What is the grand total of that column?
225,044.
And just leave your hand covering up the rest of that table. From that, I want the number that was in 3,000 to 3,999.
16035.
Does everyone see where I'm getting those numbers? G wants to know if they are independent. The definition of independent, there's different ways we can do it. One option is to realize independent means they have no impact on the other. So the probability of one thing happening is the same as that probability if something else already occurred. All right, we are checking post-term and 3,000 to 3,999. So if we look, in part F, we just found the probability that they were in that wage group given they were post-term. If these are truly independent, that would have to be the same as the probability of just being in that weight group. Okay, on part F, we just found that probability to be 0.7125. If you look 3,000 to 3,999, we did that in part B, and we got 0.6576. Are those the same? No. Since they're not the same, that tells me these are not independent. The probability of that baby being in a certain age group changes if they are post-term versus preterm. Does that make sense? Do we need to look at number 11? I did have several people ask me questions on that one. We're okay with that? They're independent, so it's just the 0.18 to whatever power. Number 12. Because of a packaging error, a case of 12 cans of pasta sauce contains 5 traditional and 7 meat sauce without labels. Okay, so there's my 12 sauces. Part A. We are going to randomly select 3 cans. The probability that all are traditional. So I need 3 traditionals. What's the probability the first can is traditional? 5 out of 12. There are 5 traditionals out of the 12 total. If I take out a traditional, what's the probability the next one is traditional? If I take out that traditional, what's the probability the next one is? So if we multiply those, we get 0.0455. Part B. What's the probability that exactly 2 are traditional? This is the one that might have got you a little bit. If there's 2 traditional, it could be I took out a traditional, and then a meat sauce. But is that the only way I can do it? No, I could have gotten a traditional and then a meat and then another traditional, or meat and then 2 traditional. So those are the only ways I could get three cans where 2 are traditional. So or means we have to add. So I'm going to calculate 3 probabilities and add them together. So traditional, there are 5 out of 12. If I take out that one traditional, now how many? Okay, if I've taken out my 2 traditionals, what's the probability of a meet? Okay, so that's one option. Or the first one being traditional. So we're back to the beginning. 5 out of 12 are traditional. If I take out one of those traditionals, there's still 7 out of the 11 cans that are meat. If I take out that meat, now 4 out of the 10 are traditional. Or, if the first one is meat, there are 7 meats out of the 12 total cans. If I take out one of the meats, now there are 5 traditional out of the 11 cans remaining. If I take that one out, we have 4 out of 10. So put those in, add them together, we should get 0.318. Is that one okay? If you are having trouble with those, I recommend kind of writing out, like drawing a picture, or like I just did, T's and M's to kind of visualize what's happening. So part C, what's the probability that none are traditional? I only have 2 options. It's either traditional or meat. If none of them are traditional, that means all 3 are meat sauce. So there are 7 out of 12 that are meat. If I took out one of those, now there's 6 out of 11. If I take out one of those, now it's 5 out of 10. We multiply and we get 0.1591.
Is that not one where you can just add up the other ones and subtract?
No, because we never did the case with one traditional. If we had, then yes.
I was
that would
wondering
work.
how that got to 8, because there were 3 options.
Okay. Problem 13. I wanted an example of each of these. So we have 3 types of probability: subjective, classical, and empirical. Okay, what is subjective probability?
Subjective is what our professional thinks.
Right, professional opinion. So an example of that might be if I said 30% chance of rain. Okay, it's not just a total guess. You know, there are reasons, but could you take 2 different meteorologists and they not agree on that? Absolutely, because there's a bit of personal opinion there. Okay, what is classical probability? Yeah, it's basically just what it should be. So if I roll a dice and there is a 1 in 6 chance of a 5.
That's what I wrote.
Really?
Yes.
I can see it from here. So I know there's only 6 sides to the dice. One of them is a 5. So it's just straightforward like that. Empirical is based on past data. So it's based off not necessarily what could happen, but what we have seen happen. So what would an example of that be?
5 out of 10 Americans don't like mushrooms. 50% of the American population don't like mushrooms.
Okay. So based on a survey, five out of 10 Americans dislike mushrooms. So empirical is what we expect based on what we've already seen. Okay, there's some other kind of data, or it might be that I roll a dice 100 times and I get a 5 times. I might say there's a 5 out of 100 chance of getting a 5. That's different than the classical. Classical, I'd say 1 out of 6. Empirical is what really happened when I did my experiment. So empirical is kind of based off an experiment that happened. Let's look at number 15. So, I gave you a frequency distribution. So we had x and a frequency. So 4, 5, 6, 7. Part A says make the probability model, including the xp of x and x squared p of x columns. So, probability model is basically where I just make a table with the probability. Now, you probably create a new table, so you probably don't have the frequency in there. If you do, that's fine. But we need a column for probability. And then I said also give me xp of x and x squared p of x. Okay, so if we add them all up, how many do we have total? 76. So, to get our probability, you take your frequency divided by 76. So 20 out of 76 is 0.2632. Then, xp of x, I'm taking 4 times the 0.2632. X squared p of x, I'm taking 4 squared, so 16 times the 0.2632. Do you guys know where I'm getting those numbers? So the next one, my frequency is 18. So 18 out of 76 is 0.2368. Next column, I have to take that times x. So 0.2368 times 5. And I take it x squared. So 5 squared is 25 times 0.2368. We get 5.92. So remember, next one, our frequency is 22. So 22 out of 76. 0.2895. Take that times 6. And 6 squared times the probability. Get 10.422. The last one, 16 out of 76. 0.2105. So 7 times 0.2105. And 7 squared times that. So this table is just a lot of calculator work to get that. Are there questions about how I got any of those numbers in our table? So part B wants us to graph the probability distribution. So we are just making a rough sketch here. My x is my x-axis, our probability is the y. Okay, so I'll count by 0.05s. Okay, my x's, I only need 4, 5, 6, and 7. You can count by ones. So, at 4, the probability is 0.26. So we usually just did it. There's different kinds of graphs you can make. The easiest option is just like a line. going up. At 5, it was 0.23. 6.28, so it's almost to the 3. And 7 is 0.21. Part C, look at your formula sheet. It asks for the mean. I did not tell you that this was binomial, so this is just a normal probability distribution. So if we look under chapter 6, the first bullet, the mean or expected value of a discrete random variable. This means the sum of x times p of x. So I have to add up that column on my table. So I'm just adding those numbers. And we get 5.4478. D asks us for the standard deviation. On your formula sheet, there's 2 formulas for it. The easier option is going to be the second one, because it says the sum of the x squared p of x's minus our mean squared. So we add up the x squared p of x's. We're adding up this final column. What did you get when you added all those together? I had something different.
30.867.
That's what I got. Did you by chance add the last one twice? Because you're off by about that much. Minus the mean, which we just found in part C, squared. So then I'm just typing that entire thing into my calculator. So the square root of all that, we should get 1.09. Questions on that one?
Do you want us to write the frequency on it, or?
No, I gave that to you. I just copied it down because I was showing where it came from.
I didn't know if that was points if I.
No, you would not. Okay, 16. Let's take a look at this one. We've done some like it. We had a class example and a couple in our homework. If you know what you're doing, they're not that complicated, but otherwise it's kind of confusing. There's probably going to be one very similar to this on your test tomorrow, because I've kind of given you the same type of question several times, so that's probably the type I'm going to put on your test. We have a life insurance company sells a $250,000 policy to a 20-year-old female for $300. The probability of the female surviving the year is 0.999544. Compute and interpret the expected value. Underline that, expected value. I'm asking you to find expected value. If you go to your formula sheet, do you see expected value anywhere?
Yes.
Yeah. On chapter 6, that first bullet, mean, and then it has in parentheses expected value. And it tells us, this is the mean, it's the sum of the x p of x's. So, we need x, we need p of x, and then we can find the x p of x. Okay, x is the value, right? So, the value to the company. If the female survives the year, what's the value to the company? $300. They make a profit. And the probability that that happens is?
0.99954.
Okay. If you want, you could go ahead and do your XP of X. You just take 300 times that. Let me get this number. If the woman does not survive the year, then the company has to pay $250,000. So they are losing money, but they don't lose a flat $250,000. How much do they lose?
Negative 2,000 or 2.97.
Okay, and why is it not the full 250?
Because they already got it.
Right, they already got paid the 300. The probability of that is 1 minus the probability that the person survives the year. So we get 0.000456. Okay, so we multiply those. We get negative 113.8632. So our mean is just adding those. And we get,
186.
so they have an expected value of $186. That means if they insured millions of people, they would expect on average to make $186 per person. Does that work if they only insure 10 people? No, because if one of the 10 people does not survive, they have lost everything. Okay, it only works if we have a lot of people on the plan. All right. Is that one okay? Number 18. So the probability a random patient who visits the ER will die within a year is 0.05. A. What is the probability that exactly 1 of 10 will die within the year? So, when I'm looking at this, does everybody have the same probability? Do we have a set number of trials? Do we have, are those independent? Yes, so this is binomial. Okay, so remember the binomial, we can read them from the table if they're nice. If not, we have to use the formula. We want exactly 1 of 10. So I'm talking about 10 for my grand total here. My x is 1. Is this on our table? If I go to the binomial table, n of 10 is on here, p of 0.05 is on here. When x equals 1, we get
Wait, did you work that one?
p. Probability that fewer than 2 of 25. So now my n is 25. Fewer than 2 means x could be 0 or 1. Is 25 on my table?
No.
No. So we have to use our formula. So if you forgot, you can look under the binomial. In chapter 6, it tells us n, choose x, p to the x, 1 minus p to the n minus x. So saying none of them, or what am I looking at? None of them die, all 25 survive. Or we could have 1, so 25, choose 1, 0.05 to the first, 0.95 to the 24th. Easiest option is to type in the first one. Remember, you have to go to Math, Probability, and CR. And then you can just do second enter and go back and change the numbers for the next one. There is some rounding error here, so if I'm already rounding them to 4 decimals, it could impact my final answer slightly, which is why if you are plugging these in, I just ask that you write down the numbers that you're using, and we get 0.6424. B, the probability that at least 2 will die. So we did fewer than 2. At least 2 is just the opposite, isn't it? That means x could be 2 all the way up to 25. So I could calculate all those, or I could just do 1 minus the probability I found in part B, because they are opposites of one another. Okay, part D. What's the probability at least 8 of 10 will not die? So there's different options, but notice, remember up here, this is the probability that the person will die within a year, right? So depending on how we want to think about it, if at least 8 of 10 will not die, what is the probability that they will not die? There's a 5%. Yeah, if there's a 5% chance that they do, there's a 95% chance that they don't. X could be 8, 9, or 10. So we can read these from our table because I'm back to n equals 10. So I tried to throw some in where you had to do by hand and some you could read from the table. So if n is 10, probability 0.95, 8 is 0.0746, 9.3151, 10.5987. Add those together and we get 0.9884. So very high chance that that happens. Part E. We now have 1,000 people. We want the mean. The expected value is the mean. If you're talking about a binomial, the mean is just n times p. We have 1,000. The probability that they die is 0.05, so 1,000 times 0.05 is 50. Standard deviation is the square root of n times p times 1 minus p. So we have 1,000 times 0.05 times 0.95 under our square root. And we get 6.8920. Alright, so some of the binomials you might be able to read from the table, some you will not. Is that one okay? Number 19. According to a poll, 60% of U.S. women believe the minimum driving age should be 18. In a random sample of 15, find these probabilities. So, is this binomial? Only 2 different outcomes. Either yes, they think that, or no, they don't. Do we have a set number of trials? Alright, so part A, exactly 10, so that means x is 10. This one is on your formula sheet. So look at your binomial table, go to n equals 15. That's the back page, I believe. P is 0.6. And if you go down to 10, you get 0.1859. B, fewer than 5. So that means it could be 0, 1, 2, 3, or 4. So if I go to add these from my table, 0.6. Okay, 0 is and 1 are both zeros on here, so I don't have to worry about those. So my next is 2, 3, and 4. Add those numbers together and we get 0.0093. Do you guys see where I read those from the table? at least 5. That means it could be 5, 6, 7, all the way up to 15. What's the easy way to do that?
Subtract.
Yeah, that's just the opposite of what we found on part B, so 1 minus 0.9907. D, between 7 and 12 inclusive. That means you include those. So 7, 8, 9, 10, 11, 12. Alright, I am running a little bit short on time, but I think we can finish it. So we would add up all of those numbers from our table. So we have 0.1181, 0.1771. Oh, I'm just adding that column. 2066, if I could write, that would help. Plus 0.859. 1268.0664. I'll be with you in 2 seconds.
That was completely the cutout.
Okay. So we add them up and we get 0.8779. Alright, so if it's nice, read it from the table. And the last one we have up here, if I can get the